Okay, so let's switch to English now. So it's a pleasure to have Roberto Marquardt, so the University of Strasbourg, and he's going to speak about quantum dynamics of thermal diffusion. So it's for you, Roberto.
Thank you, David. Hello, everybody. I'm sad that I cannot be in Paris today, but teaching load is too heavy at the moment. So it's actually my free day today, but I cannot go to Paris for just one day. But it's good that we have Zoom and then that I can address you via this medium. So Michel, thanks to you in the first place for giving this very nice tribute to Chris. I wanted to say a few words at the end of your talk, but then I thought, no, maybe we should let it be in this way. But perhaps just to mention that Chris was not only a very good person and a good colleague, he was also a very good scientist. And I was thinking, what could have become now of our science that we are discussing now in this GDR terms? What could it have? How could it have developed if Chris was still alive? So Chris and Osman, they passed away within a week in spring, and this is really very sad for us, indeed. I will talk to you about the thermal diffusion, which is to some extent quite orthogonal to machine learning and quantum computing for dynamics. But I think we can also interpret this in a way that quantum dynamics, can have some bearing also on learning how to do quantum computing or machine learning, even though the system behaves incoherently. And Michelle presented work by Chris and by herself on decoherence effects coming from the environment. And I think yesterday, Dominique also talked to us about the way how we can manipulate coherences via quantum control. I will show to you today that perhaps we can also do this quite naturally without having any environment in the neighborhood, just by looking at the evolution of a single quantum system. Now, I would like to acknowledge this work here, or collaboration and discussions with Peter Saalfrank, who triggered the discussion to me about the mean square displacement, and also others, Salvador in particular. And I was thinking also I could have taken the opportunity while Chris was still alive to discuss about this with Chris. Chris would certainly have had very good ideas to that. Sadly enough, now this is no longer possible. Of course, this is work. Part of this work is financed by INR, and I would also like to acknowledge funding from INR in this occasion. So, okay, why is it not working? Okay, I will talk essentially about wave packets, so a time-dependent wave function that, as you can see here in the first line, can you see the cursor? Is it big enough? Yes, yes, I can see it even myself. Yeah, so a wave packet will be composed, set up as a superposition state of time-independent states, and the best choice for time-independent states, these are spectroscopic states or stationary states. And the time-dependent coefficients here, I can split them also as being given by some positive amplitude, square root of Pn. Pn would be the population of that state. Factor an exponential of a phase function, of time-dependent phase function. Now, in coherent control, this is what Dominique was, I think, explaining to us yesterday. I couldn't attend it, but I know Dominique's work and also Michel's work on that. In coherent control, we will try to control the outcome of certain populations of eigenstates in the course of time via the application of an external field, for instance, an external electromagnetic field, although control could in principle also be exhibited with very different means. So the population is one term, or the phase is the other term that is important to address in control. So with the aim of manipulating this wave packet to some extent. Now, I don't want to extend here my speech on this aspect because Dominique already spoke about this and also Michel earlier. But I would just like to recall that in 2012, together with the group in Dijon, we did some calculations on the enhancement of tunneling in ammonia in a six-dimensional calculation, so a full vibrational calculation of ammonia using MCDDH, and we could show that we could really do quite nice work in controlling the enhancement of the tunneling of ammonia. And in 2019, we published a work together with Attila Sazar and Martin Quack on the full 9-dimensional control of ammonia tunneling, so including also rotational motion, where we could show that with an external linearly polarized field, we could enhance or even suppress totally tunneling in ammonia. So this are examples of quantum control that we can do. And of course, we know many more possibilities today. Now, quantum computing, before I go on, really relies on the exploitation of the time evolution of the phases in this wave packet dynamics, right? And it really goes way beyond the simple qubit that people normally use nowadays for doing quantum computing. We can really exploit this aspect in going into the superposition of many states, so not only two states, and there some additional difficulties or opportunities will rise, as you will see. Now, as Michel said, a key aspect in addressing quantum computing is incoherence or coherence, right? And we really need to understand also what does incoherent quantum dynamics mean. And on the left-hand side of this figure here, you see the wave packet that represents a simple variation of a chemical bond. So X would be the coordinate of that bond. And on the left-hand side, you see here the evolution of this wave packet during the first, let's say, 100 femtoseconds of excitation. Typically, that would be for methane excitation thermally, right? As a function of time. And here you see the coordinate, the X coordinate. A thermal state typically will be highly delocalized. So the thermal excitation will keep this delocalization, and it will remain delocalized forever, right? So we are perhaps able to excite it thermally, but it will remain delocalized. So we have essentially no control on the position of that bond in the course of time. Whereas when you use a laser, and this is shown here on the right-hand side, typically after some time, so this is the time interval between 8 and 8.1 picoseconds, so again a 100 femtoseconds time interval here. If you use a coherent laser that is tuned appropriately to the vibration frequency of the bond, we are in principle in the position of generating such a coherently moving wave packet, so where we have complete control on the position of the bond in the course of time. Now, what I will address to you today is twofold. First, you will see that such a situation here, as I show it on the right-hand side, can be highly perturbed if you deal with systems that are highly anharmonic, or if you go to multidimensional systems that are completely anharmonically coupled, right? And you will see a perturbation of this coherent dynamics that enters here. On the left-hand side, I will also address the situation of a completely incoherent system, a thermal system, and I will address one function. This is the mean square displacement that as a matter of fact, can reveal some information on the coherence underlying the system via interference effect. And this idea came to my mind when I was giving a talk earlier this year, and I think some of you have already listened to that talk in the Netherlands. And I will address this point in the end of my talk. So, an apparently incoherent coherent quantum dynamics can arise if you start working in multidimensional systems. And this example here is from an old work that appeared in the year 2000, where we looked at the excitation dynamics of the CH vibration and methane-like compounds. So this compound here is essentially a methane molecule for which we had developed at that time a global 9-dimensional potential energy surface. So this is vibrations only. And where we have this substituted 3 of the hydrogen atoms here by heavier hydrogen atoms, such as to obtain here a chiral molecule, right? It will be chiral with respect to the XZ plane. And we come now with a laser, so we have also 9-dimensional dipole moment surface for that, and the laser will kick here the bending vibration in this example of the CH group, right? So the CH will bend like a pendulum along the Y direction in the first place. The laser will be polarized in the ZY plane, so perpendicular to the symmetry plane, and it will generate here, if it is bent, a complete chiral molecule, right? If I bend the CH motion out of the equilibrium, I will generate the chiral molecule. And we will see how the coupling between these modes will generate racemization, right? And this is completely coherent dynamics that I'm going to show to you. Now, if I tune the laser appropriately, and I chose here the wave number that corresponds to the CH bending vibration in that direction, 1270 centimeters to the -1, and I'm using here a monochromatic laser at 30 terawatt per square centimeter, you will see that in the initial phase of the dynamics, so when I put energy into it, so this is typically after 180 femtoseconds of excitation, right? This CH group will oscillate forth and back. You see here at 180. This is a snapshot, the 2-dimensional cut of the reduced probability density in Z and Y direction. So this is my polarization plane, right? So it is oscillating here on the left-hand side of the symmetry plane, and here at 184, it is almost on the symmetry plane, and at 8 femtoseconds later, it is on the other side. So you see, this is a completely coherent enantiomer. It is left-hand-sided at 180 femtoseconds, right-hand-sided, if you like, 8 femtoseconds later, right? And this is the same snapshot, this is the same series of snapshots now looked upon on the X and Y plane. So this is the plane where I can also see some variation perhaps of this racemization. But here at the moment, the wave packet remains almost Gaussian, right? There is a little bit of spreading and bending when it reaches the boundary of the potential during this time. The other lines that you see here, these are the central line here. This gives the average energy of the wave packet at that excitation time, and the lines between, so the inner line and the outer line give about the energy error that I have here, because this is a time-dependent wave packet. Energy is not exactly defined, so it will have some error, and the inner and the outer contour lines give this energy uncertainty. So you see the energy is in principle quite well defined. There's some energy content there, and the wave packet is moving forth and back. Now, if we go on in time, and I will now switch off the laser after 200 femtoseconds, you will see that 1,000 femtoseconds later, so 1 femtosecond later, this wave packet has become completely scrambled. This is the natural evolution of the isolated molecule once it has been excited. And you see here again a similar time interval. You see the energy content is about the same because I ceased putting energy into that. So I have the same contour lines here, more or less. And within 12 femtoseconds here, you see you have completely lost the control on the position of this hydrogen atom here in this molecule. It is completely, it has become apparently incoherent, right? The probability density here occupies essentially all of the energetically accessible space in energetically accessible space in configuration space, both in the polarization plane as well as in the plane perpendicular to it, that is the XY plane. You see, here it is less pronounced. We still see some propensity for staying in the polarization plane, but there is also, in particular here at this snapshot here, a significant population of the configuration space outside this excitation plane. So this is an example where we have coherent racemization in a full three-dimensional quantum dynamical racemization calculation. In those years, it was difficult to do really 9D calculation. I must say, I should come back to this example here and now really use MTDDH for running this 9D simulation. But in those time scales here, 1,000 femtoseconds or so, 1 picosecond, the other degrees of freedom hardly play a role here. So the dynamics is essentially governed by these 3 dimensions of the CH group that I'm looking at here. This is for the molecule that I called CHD2T, right? So where I have 2 deuterium and 1 tritium atom here. But if I take the other molecule, where I replace 2 hydrogens by 2 tritium isotopes and 1 deuterium, I will obtain here a different picture, interestingly. I also see this racemization, in particular in the polarization plane, due to the anharmonicity of the CH stretching vibration, which is strongly anharmonic, as you can see from this bending here. But in the bending space, or in the XY place, the X coordinates, or the plane perpendicular to the excitation plane, is hardly populated. So I see again here a racemization, but it is only 2-dimensional. And this is a consequence of the complicated coupling that you have in this molecule. The CH bending vibration does not couple equally in the 2 isotopologues. Yeah? So there is an interesting variance here, isotopical effect on this dynamics. Now we can have a closer look here at the populations of these left and right states. So I look here only at the right states. So it is completely coherent dynamics. You see this population dynamics has these beatings, as Chris also calculated them for the I2 molecule, as Michel so nicely showed. There is some apparently loss of coherence. And then after some time, there's also some regain of coherence here. And this is fully due to the anharmonicity of the system. So in Chris' work, there was the influence of the environment, the helium atoms. Here, there is no helium atom at all. This is only the anharmonic coupling that is trying kind of scrambling our knowledge and our control of the dynamics. On the right-hand side, you have the other molecule where you have 2 tritium atoms, which is only a 2-dimensional racemization. And you see here this loss of coherence, if you like, is less pronounced because this is only a 2-dimensional evolution. So somehow we conserve a little bit better coherence here. So all this beating, this is well understood. This is the CH stretching vibration that we see here. So I would like to conclude this first part where I mentioned dynamical chirality, the concept of dynamical chirality in methane isotopomers as a time-dependent but spatially localized molecular structure from coherent, fast excitation of semi-classical molecular vibrations within 10 intense laser pulses. And an initially periodic stereo mutation between the left and right forms is gradually replaced by a quantum dynamical racemization, and the origin of which is delocalized intramolecular vibrational redistribution. So we worked a lot about this concept of IVR in those years. And this delocalized IVR is not necessarily total to up to typically 10 to 100 picoseconds. It means that the coupling is not necessarily always such that I will completely scramble the probability density throughout configuration space. This has some important consequences on the ultrafast racemization kinetics, but as I will discuss in the end, also on quantum computing. Now I come to the second part, which is this mean square displacement topic. And before going to that, I would just like to recall how we understand diffusion in general terms from classical mechanics. So the mean square displacement, which is defined here by this equation, right? This is a statistical average. This is the average, statistical average is described by these two brackets here on the left and right, of the square of the displacement of the position of a particle as a function of time. Okay. So if we have three particles that are colliding, they will undergo a zigzag motion, as you can see here in the x and t plane. So a particle starts here, it will evolve freely up to this position here and that time, and then it will eventually collide, then it will return, then it will collide again, it will lose perhaps a little bit of its, it will speed up, move more rapidly, will collide again, and then will change direction and so forth. It will make a zigzag motion. And in the zero friction case, we can derive from classical statistical mechanics that the mean square displacement here must increase with the square of time. We call it also ballistic motion, at least for times that are much smaller than the typical collision time. So in zero friction case, the collision time will be essentially infinite. We will never have a collision. Einstein derived this famous formula for the classical Brownian motion that tells us when we have frictions, so when gamma, the friction coefficient is not zero, we will have a diffusion coefficient defined by this expression here, and the mean square displacement will increase linearly with time, contrary to ballistic motion, where it increases quadratically with time. So Peter Saalfrank asked me a couple of years ago whether I had given a thought on the definition of the mean square displacement in quantum mechanics. And as a matter of fact, I should say that this topic is quite unknown, yeah. And I would say it should also give rise to some controversy. I looked up at a potential definition for that naively, and I came up with this expression here, which is similar to the expression that you saw from the classical motion. But here, my x of t, it will be given by the trace of the position operator calculated with a typical member of the thermal ensemble. And here this idea goes really back to Tolman, 1938. So this is really a quite old idea, but I would say in the current literature, we are not using so much this definition at the moment. So it seems that Tolman has somehow got forgotten about this. And this typical member is given by this expression here. So this is a density matrix where this cat here is given by a superposition of eigenstates of the system. So my phi n's here are really eigenstates. The ENs are eigenenergies. And I'm using here as an amplitude the Boltzmann distribution. So as I saw it before, so this is given by this quantity here, the amplitude. But I have random phases, phi n, over which I have no control at all. So this is really quite orthogonal to quantum computing. Yeah? But I'm dealing here now with a strong superposition. So I have very many states here superimposed here on the system, not only a qubit. Yeah? And we call this also a thermal wave packet. And thermal wave packets have been widely used also in the literature, and also by Chris and together with David Tanner. So a typical thermal wave packet for a particle in the box is very similar to the picture that I showed to you before, right? It is completely delocalized here. So if this here is the box, a thermal wave packet will be completely delocalized as a function of time. And one can hardly imagine that we can extract any useful information on the position of the particle or even on the mean square displacement out of such a wave packet. Now, I will give you the result without giving the derivation for it here, but I have published it last year, so you can look it up there if you like. The quantum mean square displacement of the thermal particle, as I defined it before in a general term, can be shown to have this closed formula given here on this slide. So I will go through the individual terms of this formula here. Q is the thermal partition function, so I can calculate it. I have here sums over n and j, and n and j are quantum numbers of my eigenstates. The energies of which are given by En and Ej. And here I have the thermal coefficient, 1 over kBt. Then I have here a factor that is my matrix element of the position operator in my eigenstates. Right? And in the end, I have these beatings terms here, so a sine square of the energy difference between two eigenstate energies times the time divided by 2 h bar. Now, this naive formula that you see here has very interesting results. And I will show to you only one result at the moment. If you look at this mean square displacement of a free quantum particle, so a free quantum particle moving without friction, I can repeat these calculations also with friction. So we will do that in collaboration with Jean-Christophe Tremblay, also working on open systems. And perhaps, Michelle, your talk, recalling Chris' input, and that gave me the idea we should really talk about this in this respect, to include friction. But if we leave out friction, you obtain this very interesting result for the mean square displacement as a function of time. And I'm plotting this result here rather than showing to you the equation, which is also very simple and put here. I plot this equation here, this function, in terms of my natural time unit, which is the thermal time, given by h bar divided by kBt. And my length unit here is the de Broglie wave, thermal de Broglie wavelength, given also by this expression that you see here. So this is, of course, mass and temperature dependent. And what you see here is that, so this is, first of all, a very neat line, right? You could hardly imagine that you could get out such a situation from a completely scrambled wave packet. But initially, it grows quadratically, as we would expect it from classical mechanics. But as time goes on, it evolves into a linear function. So as time goes on, this mean square displacement gets the characteristics of Brownian motion. And I repeat, I'm dealing here with a situation that has zero friction. Right? So this is an interesting result per se. Now, this is for a this is fully analytical for the free quantum particle. What happens if we put this particle now really in the corrugated surface? And this is a result for the carbon monoxide adsorbate on a copper surface, and we are studying the diffusion of these adsorbates in our INR project together with Fabien and Jean-Christophe. And on the left-hand side, you see a potential energy surface, or a cut of the potential energy surface. This is the 60 potential energy surface for carbon monoxide, moving only along the XC direction. So the XC direction would be the motion. I start with the carbon monoxide here. It will go over the barrier that you see here, and then it will go to the next stable site here. Okay. So the barrier has this height here. If I relax the potential in 6D, it is about half an electron volt. And if I include now the 0-point motion, I get the upper line as you see here, and the barrier reduces to about a quarter of an electron volt. Yeah? So the molecule could thermally diffuse from this side to this side here. Some experiments carried out by Tönnies in the last century give that this barrier here has about this height here, and this is about the same height that we obtain also here from our ab initio calculations. Now, this point has some controversy at the moment. I don't want to go into this point here today. I would just like to show to you the result that we obtain if we imply the very same idea, but do this now fully numerically using MCDDH. And I really want to go 6D to show how this evolves for that. This is the black line that you see here. So the mean square displacement for carbon monoxide and copper has this rather strange behavior that you see here. So this is, of course, no longer very coherent, if you like, but it has this kind of beating that you see here, okay? The red line is the line that you obtain for the free particle. So you see the effect of corrugation for a free carbon monoxide molecule. So if the potential, the barrier would be 0, right? No friction. And here we have no friction, but we have a barrier. So the mean square displacement is, of course, inhibited, right? So it will not grow as importantly, and it will undergo these oscillations. But there will also be a very, very small linear increase of the median of these lines here. And the slope of this here is about 1.2 times 10 to the minus 3 a square picoseconds. A is the length of this, so it is the kappa distance here. And if you compare this now with experiments that are carried out in Oxford, in Cambridge by John Ellis, they did helium scattering experiments, and they obtain here a diffusion coefficient for this motion, which is on the order of 0.6 angstrom square per nanometer. And if I interpret now this continuous slope as a diffusion line, because that would be a linear increase of the length, I would obtain 4 angstroms to the square per nanosecond, which is the same order, but you say perhaps a factor of 10 larger only. And I think for completely theoretical results that has no bearing on friction, this is not such a bad comparison. So I would like to conclude here for the moment being. On this part, the quantum mechanical definition that I present here can be used and was used here to evaluate the mean square displacement in the short time approximation, so before really friction sets in. And the result has characteristic elements of the jump diffusion model by Chudley and Elliott. I didn't discuss this here today with you, but we can show that this is so. But so essentially, the mean square displacement is governed by tunneling and potentially other quantum mechanical effects. And it shows the signature of Brownian motion even for short times. And this, to my end, is really very closely related to a strong interference effect of these eigenstates, which survive decoherence. Right? So perhaps we can also learn from this decoherence effect, from the survival of the interference effect for quantum computing. So I will conclude here in the general terms on that. Quantum computing relies on the knowledge, as we have been evoking during the last few weeks, and eventually also the control of the relative phases, the coherences of quantum states and their time evolution. I showed to you that in a multidimensional, in particular anharmonic system, as I discussed it here today, the coherent quantum dynamics might become apparently incoherent. Yeah? And that could, to some extent, also perturb the using of quantum computer if you really go to many, many states that are coupled. But even in incoherent time evolution, so when I look at thermal situations, quantum interference effects are potentially exploitable for the development of quantum computing via macroscopic quantities such as the mean square displacement of a quantum particle. Now, I should say, it is not known to me that experimentalists have measured this mean square displacement, in particular not in a short time evolution as I presented to you here. But I think that that could be a way to go, that we could learn out of this how to run quantum computers, even if we have some prohibiting them. And so thank you much for your attention. Any questions? I cannot hear you. I cannot hear you.
Okay, so we have a problem with can you hear me?
Yes, now I can hear you.
Yeah, we have a problem. At some point we lost connection.
Oh, so, you didn't hear my whole talk then?
No, it was the last minute.
Okay.
So do you have question? Yeah, Olivier.
Hi, Roberto. This is Olivier speaking.
Hello, Olivier.
I was wondering, in the definition that you gave for this mean square displacement, you proposed that definition, and you were showing simultaneously the evolution, the numerically calculated evolution of a wave packet. And I was just wondering, should I understand that this mean square displacement is indeed describing, if we would calculate that quantity on the numerical wave packet that you have calculated, would we get the same number? That is, this mean square displacement indeed describes the variation of that wave packet in time?
Olivier, it is exactly the mean square displacement underlying that wave packet.
Okay, but the point is that you provided this analytical formula, but it is the point is that then it is amazing that this analytical formula is indeed describing this extremely scrambled wave packet in such a simple way. This is your message, right?
Yes, this is exactly. Is astonishing, but I recall, Olivier, that this wave packet here is now a snapshot, very specific choice of the random phases, right? So I will have perhaps here a superposition of 1,000 states, with 1,000 random phases, and they will generate this wave packet. Now, if I take another superposition with, again, new 1,000 random phases, I would have a slightly different, but also very irregular wave packet. Now, if I average over all of these phases, over all of these wave packets, what will I get? I will get a homogeneous distribution in configuration space, telling me that in average, my particle will have the same probability in being to the left or to the right or in the middle, the very same probability. And furthermore, that probability density, the average one, will be time independent, okay? This is exactly what you get from, if you take the average position of a free particle in a thermal state, it will be time independent. It will not evolve with time, and it will be everywhere with the same probability. Now, this is not telling us what happens if I take now this quantum definition of the mean square displacement as a time function. Not get something that is time dependent, we'll get something that evolves with time. And actually it evolves in this very fancy way. Now, when I published the article, Olivier, I will just be brief on the answer. One of the reviewers asked, how would you measure this? And the measurement procedure would be indeed a complicated one. We should really be able to target the very same particle at one time and at the second time without perturbing it. The measurement itself will destroy the wave packet. So you see, so there is a complication really in trying to measure this in effect. There are ways of doing that in detail, but these will be complicated experiments.
Okay, thank you.
Other questions? I've got one question, therefore.
Yes. I cannot understand you, David. Shall I stop sharing I cannot understand you. Nikolai is trying to ask a question. Nikolai, you have to unmute yourself. I cannot hear you. Now I can hear you.
Yeah, can you hear me now? Hi.
Yes.
Yeah, good to see you.
Hi.
Thanks for the presentation. I'm not sure that everyone hears, but okay, I'll ask my question. So in this diffusion of CO on copper, do you include the phonon couplings in your potential?
No, not in this simulation. But we are planning to do so. Of course, this is a long ongoing project. And the first idea, you're fully right, Nicola, if you include phonons, we will naturally also include friction, right? And also we would include a bath to it. There's several ways of doing that. And this would have also a bearing on the long-term diffusion. Now, the graph that I will repeat perhaps here, the graph for everybody that he can see. So this line here that you see, this is an evolution that takes place in the first 10 picoseconds. And now we know from experiment, but also from old theoretical work by Tully, that the friction friction effects would set in only after 10 picoseconds. So the time evolution of this quantity later on here would be impacted by phonons typically.
Okay, but that could explain the difference between the experiment and your value, right?
Of course, yes, truly, yes. This is certainly so. I'm looking forward to include that to approach better the experimental result. Sure, yeah.
Okay, great. Thank you again.
Further questions? I cannot hear you, David.
And can you hear me now? This is Thierry speaking.
Hello, Thierry. Yes, I can hear you.
So very nice talk. Thank you. No, that was just because at the end of your talk, we could not really hear all your comments on the last slide about the link with quantum computing and noise, and that coherence could be.
Okay. Yeah, I will perhaps then very briefly repeat this. So, of course, we know that we need to keep coherence to some extent. Now, we can. I said that we could lose coherence apparently if the system is multidimensional and strongly coupled, right? Yet, depending on the nature of the coupling, we could again gain at least part of the coherence and work with that. Now, regarding the thermal wave packet, I said that we could perhaps exploit quantities such as the mean square displacement or other quantities that are typically microscopic quantities that that have some background now on the quantum dynamics of the individual atoms and molecules, but we could exploit it to also pass on information for a quantum computer. And when I say that, I will just go back to this figure. You see, Thierry, that even this thermal state I mean, for the completely flat potential, this quantity here really goes linearly. It increases linearly, right? So this is the exact motion, by the way, the dotted line. It increases linearly. This is from analytical motion. And this is something that we could exploit. We could take in, this is a very important piece of information, that it increases linearly despite the fact that the wave function is completely erratic. Now, if you put the molecule on a surface and let it evolve, you see it will have a similar situation. This is the mean quantity, right? But it will have here these beatings, yeah? And we can rationalize that the beatings here, they are related to the curvature. I will now show this line, to the curvature of this potential. So the curvature of this potential here, it is not really quadratic, but it will give rise to vibrational frequencies here. Okay, so it is not harmonic, it is highly anharmonic, but it will evolve here like a harmonic oscillator, right? So the lines that you see there and here, they can be rationalized by this harmonic potential that you have in each well. And this could perhaps to some extent also be exploited within the development of a quantum computing. If you put molecules now on a surface and you determine now really with time resolution, the mean square displacement.
So it is in fact linked to the concept of logical qubits that there was a talk this week. Yes.
Yes, exactly. Yes. Mm-hmm. Okay. But that would be a qubit that is now obtained from, let's say, a thermal average.
Okay, thanks.
Other question? Okay, so if not, let's thanks again, Roberto. And
thank you for listening. Yes. Mm-hmm. So it was nice to talk to you and to hear your questions. Yeah. Mm-hmm.
Say it again. Okay. We lost it. So
no, I'm still here. I'm still here. I'm hearing.
No, I said that we just thank you again for your talk. And
you're welcome. Yes.
There was no other question.
Good.
Okay. Thank you, Roberto. And
thank you.